Hello, Andy Schweitzer here. A little video on our properties of matter, moving to the section on liquids. And in this case, the question is what makes something liquid? Um, for solids, as we've mentioned, solids are locked together very tightly. There's very strong interconnections between these molecules, whether those interconnections are ionic bonds. They could be covalent bonds if it's a network covalent, or it could just be a weak intermolecular attraction. So far, only when we talk about that would be hydrogen bonding, and we'll look at that. No, either way, we already talked about that. So, in this case, for something to be liquid, would mean that basically the interactions between these two particles are relatively weak. That means we have now crossed out an option, put next here, of ionic. Ionic is out. It cannot be an ionic bond, so these are way too strong. These definitely would be a solid. The network covalent, even stronger attraction, so that thing definitely is a solid. That thing is going to be out. So at this point, we're looking at a molecular or substance. So it's covalently bound with weak intermolecular forces. Okay, so this is going to be something that's covalent. Okay, we're talking like water, carbon dioxide, two nonmetals, sulfur dioxide, could be carbon tetrachloride. So there's all sorts of these different chemicals. Could be propane, and they sell that right now for home heating purposes. In fact, in 2014, which it is now, there's a shortage, really causing the price of propane to go through the roof. But either way, LP, liquid propane. So depending on the intermolecular forces, it could be a liquid. Okay, now we're talking internal versus external forces. So at this point, internal forces is what we just talked about, the actual bond type. So we're talking hydrogen bonding. Okay, and so we have a molecule, and there is some covalent bonding on the inside of this thing, potentially another covalent molecule, covalent bonding on the inside, and for some reason we have a highly electronegative atom on one side and not so much on the other side, creating what we call a dipole. This dipole will be attracted to other dipoles, all right, and there is a Coulombic attraction between positive and negative. All right, and the other one we're looking at here is external factors. Okay, for the external factors, of course, we're talking about temperature and pressure. You will notice that we used a triple phase diagram to kind of explain this a little bit, and they kind of look like this, generally speaking. This has got an arrow on it. So you'll find that this is pressure and this is temperature. So you'll notice this is quite vertical here, and that's because as I raise my pressure, it's not really affecting the solid liquid phase very much. Now, gases, on the other hand, are drastically affected by pressure. A slight increase in pressure really causes changes between these things here. So either way, temperature as well. It's a very unique area here where there is a very small window, and so this is just an example. This could be smaller even yet. These lines can change as well. But either way, there's a small window where this thing can be liquid. Okay. Now, one thing we'll focus on here is that properties. One unique property of a solution that we'll concentrate on here, okay, is the fact that things dissolve in liquids. Okay, so we have a picture, okay, beaker, and I take something, let's say, like sucrose, which is C12H22O11, versus, let's say, another compound, let's go with everyday table salt, NaCl. I fill this up with water. Okay, now a couple terms here. The water, H2O, which is polar. It's got a positive area here, negative area here. Same thing here. This is called a solvent. In this case, it's a polar solvent. But this stuff here is the solvent. What I'm going to dump this in here to attempt to dissolve it, we call this stuff the solute. Okay? When you put the solute plus the solvent, we get the whole mixture of stuff, which is referred to as the solution. Okay. Now, only so much stuff can dissolve in any of these solutions. So as I start, I'm just going to use this molecule here as an X. Okay. And as the stuff starts to dissolve, there are charged parts of this molecule, and they start to huddle around the water molecules, and eventually it gets saturated. So saturated is another term. This is the max solubility. Now, what are the factors that affect solubility? If you want to dissolve more stuff in a particular solution, what are some of the things that you can affect? Okay. Now, on an atomic level, okay, it's, there are, again, Coulombic attractions. This thing here has positives and negatives. This water has positives and negatives, and the attraction between these things is purely governed by Coulomb's law. Force attraction equals the charge of the cation times the charge of the anion divided by distance squared, and there is an equalizing factor in here. Either way, people often say likes dissolve likes. Charged particles go mix up with charged particles. You have to understand that this is the reason why. The solute is attracted to the solvent by electrostatic attractions. Now, as this sodium chloride dissolves, I want to point out that ionic compounds dissociate. This is negative, this is positive. The cations will be holding around the negative electronegative atom, and the chlorides will be huddling around the positive area. The way I'd write that is like this. This thing, very important property, which is not the first time we've heard this, but it dissociates in solution. A covalent compound does not do that. An ionic compound definitely will separate. These charged particles here will cause all sorts of ramifications. One of them is as an electrolyte. That means it will a solution that will conduct electricity. Alright, so if I want to get these things to dissolve here, what are some factors that I can control when dissolving them? Right? First one is temperature. Okay. So now there's a discrimination here between if I'm dissolving a solid, okay, or if I'm dissolving, let's just say hypothetically, a liquid. I'm sorry, not a liquid, but a gas. Okay. Now, a solid, okay, the temperature is one factor. Okay, and of course, increasing temperature will increase the solubility. Okay. For gases, however, and the reasons for this, I haven't never really seen a real good explanation for it, but for temperature also greatly affects the solubility of gases, but it's the opposite. As you increase the temperature, you decrease the solubility. So if I want to dissolve a gas, let's say you're making your own soda at home, and you want to put some carbon dioxide gas to carbonate it, you want to lower the temperature as you dissolve the gas in there. Now, pressure also is a factor. Okay, pressure. I will say that pressure almost no effect on the solubility of a solid. Um, we have this solid right here, and we have our liquid, we have a solid dissolved in here, and at no point can this solid jump out of the solution. So that by putting more pressure down onto this thing is having little to no effect on how much it can actually dissolve. But gases, on the other hand, much different. The gas, technically, you dissolve solution involving liquid, okay, and you start putting carbon dioxide molecules into this thing, CO2s. They can potentially work their way to the surface and then simply escape as a carbon dioxide molecule. So the pressure on this thing definitely has a huge effect. Okay, the more pressure you put down on this thing, the more that particular liquid is going to be willing to be able to stay in there. So as I increase my pressure, I'll increase my solubility. Now I will say, for example, you take a can of soda. Okay. Now there are two factors affecting the solubility of those gases inside that soda. There's a little space here on top of a soda, often referred to as the head space. Okay, not important for this class, but either way. And there's all sorts of carbon dioxide dissolved in here. Right. And if I were to lower my temperature, I would be able to get more and more carbon dioxide dissolved in there. So, but either way, let's just say it's sitting on your desk, and let's say it is closed. It has this little opening here. Okay, but at this point it is closed, and there's a pretty high amount of pressure in here. So at this point, there is equilibrium between when the gas exits to a gas entering. Obviously, this pressure is constant. Okay, it's closed, so it's not open, but it's constant. As soon as you open your soda, okay, you open this thing up, gases are allowed to escape. This carbon dioxide, this head gas, and immediately you'll start seeing bubbling occurring, go to the surface, bubbling occurring, go to the surface, bubbling occurring, going to the surface. And that's because with the reduction of the pressure above, the solubility of this gas is simply, it is simply dropping. Okay. If you were to cool your beverage and then open it, you'd have a better ratio of solubility here. Now, solubility can be measured as a ratio between stuff dissolved and total volumes, and we'll talk more about how you quantify that. But because temperature is controlling your solubility, there is another factor, another variable that we might call supersaturated. I'll put it up here by this guy. Okay, that's where you would raise the temperature. You would therefore dissolve a whole bunch of stuff to achieve a very high solubility, and then simply drop the temperature very slowly. And at this point, it's possible, although not real common, that you might be able to hold a little bit more than what you normally would be able to. And if you disturb it in some way, you would definitely be able to drop it out. Solubility is a delicate process. If you've ever made rock candy, you'd see that it's a very saturated substance and forms nice little crystals. All right, thank you very much. Dissolves. All right. Let's say, for example, we have our solution again with our NaCl dissolved in this thing. You'd want to understand that Na plus and Cl negative are undergoing what's called, they're hydrating that water molecule. We have an OH, they're just right around the outside of this thing. The chlorides are just huddling around here, And there's a pretty good attraction here. Okay. Now, when this thing dissolves, obviously gravity can pull on this thing and pull them down to the bottom. If it's stuff staying at the bottom, you'd see that it is fully saturated. But how can you remove this solute? Question. Okay. And I would say that being the process of dissolved, okay, is a very unique process. Okay, it's not just kind of hanging out there, right? Being dissolved means that it is definitely in the solution, and given time, okay, this thing will not settle out. Okay, you could filter it. Okay, will not filter. So I could put this thing through. We've done vacuum and other types of filtrating. So when I put this thing in a little Buchner funnel and I put it in there and I suck it through, all the water would go through along with the sodium chloride. It is not going to be able to be filtered out. Another way which someone else might attempt to separate two things would be what's called a centrifuge. And a centrifuge looks kind of like this. And inside here we have these little tube-like situations, and you could take a test tube and place a test tube in this thing, and this thing will also be spin around and around and around and around really fast, and anything that's in there that's not dissolved would settle towards the bottom. Okay, but if something is dissolved, it will not be removed by a centrifuge. Okay, does not settle. Centrifuge is a way of basically increasing gravity. Okay. I also would mention that when you dissolve something, generally dissolved particles do not take up extra space. So I could have 100 milliliters of water in here, and if I dump in, let's just say 20 milliliters of salt, I'm not guaranteed to have 120 milliliters of volume. The salt will actually fit between the water molecules. They're very tightly knitted in there. Maybe I get 102 milliliters of volume. I'm not going to get 120. I might maybe get 101 or 102 milliliters. So a slight increase, if any. Okay. Now, there are different things where something isn't truly dissolved. This is what we call a suspension. Okay. Now, suspension, there's apparently no T in there. Okay. Now, suspension is a situation where you just take a solution, okay, and let's just say you got some dirt, and you just dump it in here, stir it up, and you have all the stuff just floating in solution. It may look like it's totally dissolved, okay, but it's not. Give it 1 hour, and this thing just starts settling to the bottom. Okay. I also note that in a dissolved solution, generally they are clear. Okay, not always. There are a handful of solutions that aren't clear, but you see this stuff floating on here, that solid particulate? That's not the case here. It generally is clear. It would be clear blue, maybe clear green, but not.
Students, please come to the high school office.
Thank you very much.
Nick Fonspender, Bryce Monty, Abigail Broski, Ariana LaCourciere, Rachel Scheid, Alex Bonakowski.